In this video, I'll be introducing holomorphic functions. Okay, get right into it. Definition. We say f, a function from the complex numbers into the complex numbers, is holomorphic. It's holomorphic if the limit as delta z approaches 0 of f of z plus delta z minus f of z all over delta z exists for all z an element of u, a subset of the complex numbers, open. So u open. So it's in an open neighborhood. So complex plane, f between it, open set in the input, image in the output. Right? Pick a point in it, pick a point in the output. I can approach it from anywhere in this input, any direction I pick, right? Any possible direction I pick. What they look like in the output, the derivatives along those, right? They're all going to be the same. And more specifically, this is how you derive the Cauchy-Riemann equations. So that if I look at the vertical and the horizontal in the input and the output, right? And you look at the derivatives along them, they have to be the same. And analyzing this, if you watch Dr. Pyam's video, what you can get is a theorem called the Cauchy-Riemann equations. Okay, so is that f is holomorphic. F is holomorphic if and only if the partial derivative in respect to the real part, the first component of f, the first component of that is equal to the partial derivative in respect to the second component of f, second component. Okay, and that the partial derivative in respect to the second component of f, first component, is equal to the partial derivative in respect to the first component of f, second component, except you carry out a negative. Okay, what does this mean? Well, it means that if I take a tiny nudge along the first component, and I look at the corresponding nudge right there, and I look at the first component of that, that should be the same as the nudge in the second component, the vertical component. Look at the nudge there, and look at the vertical of that. Okay? And then what the second one says is if I look at the vertical component, right, and the tiny nudge there, and I look at how it goes down to the first component, that should be equal to the negative of what it looks like across that and that downwards. Across. Okay? And you can derive that directly from it. Okay, example. Example. F of z equals e to the z. Or in other words, f of x plus iy equals, we're going to have e to the x plus iy equals e to the x, e to the iy equals e to the x cosine of y plus I sine of y, right? Equals e to the x cosine y plus I e to the x sine y, right? Okay, so let's just write it like that. So f of x plus iy equals e to the x cosine y plus I e to the x sine of y. Okay, why is this holomorphic? Well, the partial derivative in respect to the first component of f, first component, what's that going to be? Well, it's going to be e to the x stays the same, so it's going to be e to the x cosine of y. That's the first component. Okay, then the partial derivative in respect to the second component of f, second component. Okay, so that becomes e to the x derivative sine of y is cosine of y. Okay, so if we look at the in respect to the first and then the second of that, so that becomes e to the x cosine of y, or just e to the x sine of y, right? And then in respect to the second, and then the first, that becomes negative e to the x sine of y. You can see that's obviously satisfied. Those are just equal. If you negate it, they're equal. Negated. And that's what you want. Okay, so it's holomorphic on all of C. Is there another example? Well, yeah, it's cosine of y and sine of y, because they're directly related to cosine of z and sine of z, because they're directly related to the exponential function. Okay, but sometimes it's not on all of it. Okay. Now you may be wondering, why does this matter? Why do we want this to happen? Well, it's because if you don't have that derivative well defined, you can't have partial derivatives well defined. You can't have any of this where it's all well defined. And it's very useful to have that derivative in our banks. Okay? And that's it.